Advent is the first 24 days of December, leading up to Christmas. During this time, some hobbyist computer programmers do Advent of Code. That's a set of programming puzzles held annually since 2015. I instead spent Advent working on one big puzzle, an emulator. An emulator is a program that takes a ROM image and button presses and produces the pictures and sound that the original console would make. A game console is a special-purpose computer. Like other computers, it has a central processing unit, or CPU. The CPU reads what buttons are pressed, calculates the positions of game objects, and tells the graphics chip what to draw. So the first thing I needed to write was a set of routines that would simulate an MOS 6502 processor. The 6502 was used in computers around 1980, such as Apple II, Atari 800, Commodore 64, BBC Micro, and the Nintendo Entertainment System. I wrote this in C because Python's interpreter is way too slow and I wanted it to run on machines with no Rust or Java compiler. The first thing to do is load the ROM image into the computer's memory. Fortunately, I had already written a C function for another project that reads an entire file from the disk into RAM. An NES program has three parts: the program code, the character data, and a description of support hardware on the cartridge circuit board. Programs are commonly distributed in a format called INES, first seen in an early emulator by the same name, so I needed to parse the INES header and extract the three parts. Most computers since the early 1990s have used 32-bit numbers. This counts up to 4 billion. PCs from the 1980s use 16-bit numbers that go up to 65,000. The earliest emulators ran on 16-bit machines, but by 2025, all my computers had been 64-bit for a decade, and I didn't feel like going to all that trouble. So to make sure the program is built for a 32-bit or bigger machine, I added a static assertion to the program. I tested the assertion by deliberately getting it backward and making sure the correct error message was printed. After having been in the NES homebrew scene for over 2 decades, I knew much of the INES header by heart. I still needed to look up details on NestDevWiki. A feature of INES called Trainer is meant to represent ROM hacks to run copied games on early RAM cartridges made by Front Far East. I considered Trainer obsolete and did not implement it. When a function ends, it's supposed to dispose of resources it owns, close files in Windows, free memory, and the like. Otherwise, it produces a leak, leaving an allocated resource inaccessible. In a few years, C compilers will get a defer statement. This lets a function clean up resources it owns when it ends. Until then, I use the old-fashioned way, go-to. A 1968 article by the late computer scientist Edgar Dijkstra scared a lot of programmers and teachers into avoiding goto. It turns out that forward goto is a lot easier to prove safe. It's common to use forward goto in C for code that cleans up resources. When using goto for cleanup, be sure to initialize all pointers. The cleanup code can use null pointers to know what not to clean up. I added logging to reassure myself that the parser is working. Logging, also nicknamed printf debugging, can be easier to set up than a full-step debugger like GDB. Before I wrote a single line of code, I started to write tests. This is called test-driven development. I had a set of inputs and expected output for each, and I used that to validate the behavior of my program. Decades ago, Kevin Horton made a 6502 test suite called nestest. It executes 9,000 instructions. There's a log of what the state of the processor needs to be before each instruction is run. If the state after an instruction doesn't match what's in the log, that's how I know I need to fix a defect in the CPU. Next, I needed to write a function to parse this log, and the log is another resource that needs to be freed at the end. String handling in the C standard library is low level. It's considered kind of icky nowadays to set a maximum line length, but I knew how long the lines are in the log of nestest. And C definitely doesn't come with a regular expression engine. This red line in the terminal came from the address sanitizer. This feature of newer C compilers stops me when I make certain kinds of mistake. It's not quite as strong as the rich compile time safety of Rust, or even the strong dynamic typing of Python, but it's the safety net that I appreciate. I was reading a line from the log file, and the compiler warned me that I was ignoring the result even when I was deliberately ignoring the result. I looked up what the result is, and I was still stumped as to how it isn't fully implied by either end-of-file or error conditions, so I ended up making it an internal error. That was all the time I had for day one. Yesterday, I started on a parser for ROM files and instruction logs. Most log data that I care about centers around a colon. The register name is before the colon and the value is afterward, starting to capture some data from the first line of the log. Register values and timing values will help. With the log parser mostly done, I proceeded to make a structure to hold the state of the CPU and the memory connected to it. Both the machine and a log line contain a set of CPU registers. I might as well use the same structure for both. Let's give this machine some RAM. The 6502 has 151 official opcodes, meaning instruction byte values documented in MOS's datasheet. There are 256 different byte values. That leaves just over 100 missing numbers. The first 5,000 instructions of nestest test official opcodes, and the other 4,000 test unofficial opcodes. These result from don't care values in the 6502's decoding logic. Many of them combine parts of two other instructions. Only a handful of NES games actually use unofficial opcodes. A test ROM uses instructions to test other instructions. This means that the first instructions I add won't get me very far into the log, while later instructions will get me much farther. I estimated that progress would vary as the square of effort, that twice as much time spent on the CPU would knock out 4 times as many lines of the log. Then it would become linear when testing unofficial opcodes, because those can be tested with only official opcodes. An hour and 45 minutes into the project, and I just started to write the opcode fetcher. I needed to factor out CPU register printing so that it works on both the machine's CPU and log lines. I documented the line count milestones that I'd need to hit. The CPU reads instructions from memory. It reads or writes memory once every cycle at almost 1.8 million cycles per second. I used the CPU's memory reads and writes as the core of how the emulator keeps track of time. I still had to decide how the CPU behaves when powered up or reset. Day 3 was a double header. I lost track of time while adding instructions to the CPU and ended up taking 2 hours. Every 6502 instruction begins by reading 2 bytes, the opcode and the first byte of the operand. It reads the operand just in case, even if the instruction has none, to give the circuit time to decode the opcode. This CPU doesn't do anything on instructions it doesn't recognize other than log the fact. I wanted to print a diagnostic if the test harness can't read the log. It turned out that C itself doesn't define a lot of error codes. Many well-known error codes come from POSIX, the portable operating system interface extensions used on Unix systems, and aren't guaranteed to be available apart from Unix-like systems such as FreeBSD, Linux, and Mac OS. This was the core of the test-driven development approach. Before each instruction, it would compare the state of the CPU to the expected state from the log. Then it would stop on any difference. Storing machine state and log lines in the same format came in handy because I could print them the same way. Many emulators have a great big switch statement. It lists a handler for each of several opcodes. I would be adding opcodes to the switch statement for days. I added the first ones in the order in which they appear in the log. It's a jump instruction, hard-coded on a bus with no memory. It was time to put some memory in. I started with the cartridge's program ROM and the console's built-in RAM. A set of 8 wires called the data bus carry data from ROM to the CPU. The memory charges the wire to 5 volts for a 1 or ground for a 0. When nothing responds to a read request at a particular address, you get a phenomenon called open bus. The wires hold their last voltage like weak capacitors. I modeled this as the CPU data bus being like a register. Success! I ran 1 instruction. Now to add 200 more. I made functions to handle common operations inside the 6502, such as setting negative and 0 status flags based on the last value. I got to the first store instruction and had to add writing to RAM. That got me 4 instructions in. The next was a subroutine call. I remembered what a call does, just not the order of memory accesses. For every call, there's a return, and I had to implement a stack pop for the first time. The 6502 is unusual in having an empty stack. Its stack pointer points at the next place where something will be pushed, compared to the more common full stack, where the stack pointer points to the last pushed element. An empty stack makes pushes faster at the expense of pops, because pop spends a cycle moving the stack pointer forward before reading. I guess it saves a cycle on interrupt latency. This table on NestDevWiki shows all 256 opcodes. I would refer to this a lot. No operator Operation, or no op, refers to instructions that do nothing. These are easy, so I decided to put the unofficial ones in too. And instructions that only set and clear status flags. One of them did not appear in nestest. I had to test it elsewhere. I got relative branches out of the way sooner rather than later. Not only do taken branches take a cycle longer than untaken ones, but taken branches have a penalty cycle if the taken and untaken destinations are in different 256-byte pages. The branches were similar enough to factor them into a function. I lost track of time while writing it, forcing a double header. An hour in, I was up to line 38. The bit instruction is unusual. It sets the 0 flag as if it were AND without changing register A, and it copies bits 6 and 7 from memory directly into overflow and negative flags. I think the overflow flag might be used for testing sprite 0 hit more often than for signed integer overflow. Fetching the second byte reads 8 bits into an unsigned int variable, which is 32 bits wide per my earlier static assertion. I made absolute addressing mode work by ORing the upper byte over part of the operand and repurposing the 0-page instructions. By that point, I was passing so many instructions in the log that I had to limit how many lines I was logging. Only 6 of the 8 bits from instruction PHP contain actual status flags. Bit 5 is always 1, and bit 4 tells whether an interrupt caused the push. I changed log comparison to disregard these 2 bits. There isn't really subtraction in 6502. It subtracts by flipping all bits of the value read from memory and then adding the result. That's why the carry flag goes the opposite way on SBC, with 0 meaning borrow and 1 meaning no borrow. It meant I could reuse the add function for subtracting, which is fortunate because the signed overflow bit is kind of tricky. Normally, only instructions that write to registers A, X, or Y change the negative and 0 flags. This includes load, arithmetic, and transfer instructions. Transfer to the stack pointer does not. Shifting the accumulator was the last thing I did today. I ended up 1,000 lines in after 2 hours of doing instructions.